Guten Tag. Today we will be talking about directional derivatives, which I alluded to briefly in the last lecture on partial derivatives. The functions we'll be working with will be of this form. They are real valued functions of several variables. And I'm going to begin by concentrating on functions of two variables, so I'll just put a 2 in there. Now I have two separate pictures here, and I want to say a word about each. Often when we're thinking about functions of a real variable, we want to just think about the domain itself, and then we can kind of separate off the range and think about it as living elsewhere. We do this because it's only in this special case of functions from R2 to R that we can actually see the graph. If we had a function of 3 variables, as we've talked about, you can't see the graph anymore. So this is a very special case. And sometimes its very specialness confuses us when we're trying to generalize to functions of more than 2 variables. So I want to start off, even though I'm just thinking of functions of 2 variables, just by thinking of the domain of the function, because we can do that with 3 variables or even 10 variables in a sort of abstract way. To review what we saw last time, if we have a function of 2 variables, I can think about moving around in the domain, and at any point in that domain, the function has a certain value. Like maybe its value here is 7, and maybe its value here is -2, and maybe its value here is 49. And I could always think of its value, if I wanted to try to make it a little concrete, as representing something like the temperature at that point. Anyway, if I talk about the partial of f with respect to x, df dx, at a particular point, that would mean that I start at some particular point, so it's got some value there, some temperature, if you want to think about it that way, and I want to know how the value of the function changes as I move in the x direction, in the positive x direction. Similarly, if I wanted to talk about the partial of f with respect to y, then I'd be asking how does the value of the function change if I move in the y direction. Now, in this very special case of R2 to R, I can, at least in principle, draw a picture of the graph as a surface. So I can think of the value of the function as representing something geometric, the height right there. So I could still connect it to my Calculus 1 experience of thinking about partial derivatives as representing some kind of a slope. But as soon as I have more than 2 variables for my input, it's very hard to do that. For example, if I have a function of 3 variables, so I input some point x, y, z, and I get some real number out of it, I can still think about the domain. I can think about a point moving around in 3-dimensional space, and wherever it is, this function maps that point to some particular real number, which once again I could think of as the temperature. Oh, the temperature here is 37 degrees, the temperature here is 112 degrees, whatever it is. That means the value of the function here is 37, the value of the function here is 112. But in this case, I can't draw the analog of this picture right here, because that would require somehow 4 spatial dimensions over here, 3 for the domain and 1 for the range. But I can still think about this point moving along, and at any point I can talk about the value of the function there. And I can still talk about how the value of that function changes in response to changes in the input in particular directions. Like if I'm moving parallel to the x-axis, I could talk about the partial of that function with respect to x. Or I could talk about the partial with respect to y as I'm moving parallel to the y-axis, or the partial with respect to z. And you're very used to that from the last lesson. And this all remains true even if we are talking about some mysterious function from R4 to n. Now I can't even really draw the domain for you anymore because the domain alone requires 4 dimensions. But it's not so hard to imagine that whatever this 4-dimensional space looks like, I can imagine a point moving around in that space. And as it moves around in that space, and I'm following it around, at every position, this function endows it with a certain value. So maybe the value here is 22, and maybe the value here is 78, or the temperature is 22, the temperature is 78, whatever you want to think about it. And I could say, if I specify some direction parallel to the x-axis, the y-axis, the z-axis, or the w-axis, whatever that might look like, if I move in some particular direction, at what rate is that value, is that temperature changing? Okay, enough review. Let's get back to this notion of directional derivative. The only distinction here from partial derivatives is that partial derivatives limit the directions in which we can ask for the function's rate of change. Like in the 2-dimensional case, we can look at the rate of change in the x direction, we can look at the rate of change in the y direction. Those are the only 2 partials we get. In the 3-dimensional case, we can look at the x, y, and z. In the 4-dimensional case, x, y, z, and w. In the 60-dimensional case, well, there's 60 partial derivatives. But even coming back to the two-dimensional case, I may sometimes want to know, well, suppose I'm starting at this point P, and I move from P in some direction that is not parallel to the x-axis or the y-axis. After all, there are infinitely many directions I could go from here. Why should I be restricted to just those two? If I happen to move, say, in this direction, which is parallel neither to the x-axis nor the y-axis, how does the function's value change as a result of that? If I'm keeping track of the temperature, or the height over here, if that's how I want to think about it, if I'm keeping track of the function's value, how is that value changing as I move along this line? Once again, in this special case of a function of two variables, I could give that an actual geometric interpretation over here. Like, let's say I'm moving in this direction, then to ask how the function's value is changing in response to changes along this green line, well, I can see what's going on. I've effectively restricted the domain of the function to just this green line. And so every point on that green line gets mapped to its height. So I end up with this curve, something like that. And I could say that the derivative in this direction, the directional derivative in that direction, would correspond to the slope of that curve right there. But even if I cannot interpret it like this, which I usually can't because I might be looking at a function of 3 variables or 4 variables or 100 variables. And by the way, sometimes people ask, why would you ever be considering a function of 4 variables or 100 variables? Applications like that come up all the time. Think about the field of economics. There you might be trying to model the economy in some way, and you might have hundreds, thousands of variables that you're looking at. You might be looking at unemployment rates and interest rates and certain stock prices, mortgage rates, whatever it might be, GDP, all sorts of things. You might have dozens, hundreds, thousands of variables in that context. And you might crunch all of those numbers together by some bizarre formula into some particular index, some real number that gives you some sense of the state of the economy. Well, that would be, say, a function from R200 to R. It doesn't mean economists are working in some mystical 200-dimensional geometric space, but it means that they have such a function, and we can study such things using multivariable calculus. And it is important that their intuitions not be limited to cases that they can see, like this, functions of 2 variables mapping to 1. So let's get rid of this graph right here. Okay, in fact, I think I'll get rid of these 2 and just concentrate on functions from R3 to R for a change, so that we don't get too distracted by the special nature of functions from R2 to R. In that case, just to restate the problem, I've got a point. Right? A point in the domain of the function. I'm going to draw it as a function of 3 variables, but this could be a function of 2 variables or a function of 10 variables. Whatever. I've got a point in the domain. The function has some value at that point. I want to be able to move in any direction. In this case, in 3-dimensional space, but it could be in any number of dimensions, including 2. I want to be able to move that point in any direction and say, how is the function changing? How is the function's value changing as I move in that direction? How is, if you like, the temperature of that point changing as I move in whatever direction I'm given? If I happen to be moving parallel to one of the axes, then I already know how to deal with that. That's a partial derivative. But if I'm moving in some other direction, I have to develop something new. I need this more general picture of directional derivatives. Well, that's what we'll figure out now after I move this into a nicer location. All right, first some notation. If I'm moving in some particular direction and I want to know how the function is changing in response to changes in that particular direction, I'm going to need some different kind of notation rather than just df dx, df dy, df dz, something like that, because I don't have a specific name for that direction. So the first thing I have to do is specify the direction. Well, of course, you know that you can specify a direction by giving the coordinates of a vector pointing in that direction. If I said I want to move in this direction, and I just gave you a vector lying in that direction, that would be enough to specify the direction. We're going to go one step further, though, and we're going to agree, for the purpose of computing directional derivatives, you'll see why this makes it easier in a little bit, we're going to agree to give our direction vector as a unit vector, which means that if it happens to be unit length already, great, I just write down its components. But if it's not, I'm just going to scale it down to make it a unit vector. And maybe a quick reminder from, I think, the very first video we did as to how you might do that. If I have some vector v, and I want a vector that is pointing in the same direction, but I want to change the length so that it's unit length, all I have to do is, obviously, do some scalar multiplication. I have to divide this vector by its own length, or if you want, multiply it by the reciprocal of its length. So if I were to take my vector v and divide by its own length, I'd get a vector that, of course, is still pointing in the same direction, but if it was, say, 8 units long originally, and then I multiply by 1/8, I'm scaling it down to a unit vector. Or if its length was 2/5 of a unit, and then I divide by 2/5, which is the same thing as multiplying, by 5/2, I'm scaling it up to a unit vector. Either way, when I divide a vector by its own length, I end up with the unit vector pointing in that same direction. We'll be doing that with some frequency in this particular section. So let's assume from the outset that the vector that's pointing in the direction that we want to take a derivative in, let's assume it's a unit vector. So let's say I've scaled that down, and I end up with this. And to emphasize that it's a unit vector, I'm going to call it u, and I'm going to put a little hat over it. Anyway, suppose I have my function from R3 to R, and we say, all right, I'm at this point P, and the function has a certain value there, and now I want to move in this direction. I want to restrict myself to that direction. What is the directional derivative in that direction? How do I even denote that? There are different notations in use. This is the one I'm going to use. Here it is. The capital D is for derivative, or directional derivative if you want. This specifies the function we're looking at, f, and the little subscript tells me the direction we're pointing in. It's going to be a unit vector. And if I want to specify that I'm looking for this directional derivative's value at a particular point, like my point P, of course, I would just put that in the usual way with parentheses. So this is our symbol for the directional derivative of f at P in the direction given by vector u, which we remember is supposed to be a unit vector. Good. So we know what a directional derivative is. It's just measuring rate of change of a function of several variables in a specific direction. We know how it is denoted. What we do not know is how to compute it, and that is what we must get to now. But first, there is actually one little preliminary that I need to attend to that will make our work much easier. Every function of several variables, every real-valued function of several variables, has a special gadget associated with it called the gradient of that function. And we'll be talking about the gradient in great detail in the next lecture. Here, I'm just going to use it simply as a notational device. I'm just going to introduce it purely as notation. We'll talk about its many meanings in the next lecture. Anyway, if I'm looking at a function of 3 variables, I'll start there, then what we could do is form a vector whose entries are the partial derivatives of that function in the 3 variables. This weird vector is what's known as the gradient of this real-valued function. For a specific example, let's take a function like this. We've got f of x, y, and z is x squared y plus z squared. If I wanted to know the gradient of that function, that would be a vector whose first component is the partial of f with respect to x. Well, if I took the partial of this function with respect to x, I would get 2xy. The second component of the vector would be the partial of f with respect to y, which would just be x squared. And the third component would be the partial of f with respect to z, which would just be 2z. And this strange object right here, this vector whose components are the 3 partial derivatives of this function, is what we call the gradient of this function. And there's a special notation we use for that. It's this upside down isosceles triangle. And we'd say the gradient of f is equal to this stuff. In fact, to be more specific, since we note that this gradient is itself a function of x, y, and z, I should really write this like this. Gradient of f at x, y, and z is this. If I stuck in specific values at x, y, and z, if I said like, what is the gradient of f at this point, and I put in its coordinates, I would get some definite vector. It would be a different vector if I asked for the gradient over here. Now, the gradient has all sorts of interesting geometrical meanings, which we will talk about in the next lecture. For now, though, for this lecture on directional derivatives, I'm just using it purely as a notational device. It's going to make life much easier when we come up with a recipe for directional derivatives. This notion of a gradient, of course, works for any function of Rn into R. If we had only 2 variables, the gradient would have only 2 entries. If we had 7 variables, it would have 7 entries, 1 for each partial. You will see how the gradient sneaks into our directional derivative discussion shortly. Okay, now we really are in a position to learn how to compute directional derivatives. We're going to derive a formula that works in general. So remember what's happening. I've got a function from Rn to R. We're going to use R3 to R as our case study. I've got some point, P, and I'm moving in some particular direction. And the value of the function changes. So the temperature is changing as I move this thing in that direction. And I want to know how it's changing as I do that in an infinitesimal neighborhood of that point. Well, let's let ds represent a little infinitesimal length along that unit vector. Now let me try to blow that up so I can get a feel for what ds is. Ultimately, I'd like to get ds in terms of dx, dy, and dz. So if I draw a picture, imagine blowing that thing up, I might get something like this. Now it changes by a little infinitesimal amount of x, an infinitesimal amount of y, and an infinitesimal amount of z. So on the edges of this little box, I will write dx, dy, and dz. Those little infinitesimal changes beget this little change along the vector. I could think of this length, ds, as being the length of a particular vector that lies along it. I could say that ds is going to be equal to the length of this vector dx, dy, dz. Because if I thought about that vector dx, dy, dz, if I started it at this point, I increase in the x direction by dx, the y direction by dy, and the z direction by dz, I would actually have a vector lying just like that. So ds would be its length. And I'll just keep this fact right here. I'll need it later as we derive our formula for a directional derivative. Okay, the thing we're after here is the directional derivative of f at our point P in the direction of u. Now we know what is meant by this directional derivative. It gives us the rate of change of the function f as we move in this direction. If we increase by a little infinitesimal amount, ds, we get a corresponding change in f, df, and the ratio of those changes is what our directional derivative will be. So this would be df ds. Now this is something we can actually make some progress with. The idea is I can find a way to express the top, df, in terms of dx, dy, and dz. I'll leave some room to stretch out in here. Let's think about what happens. I move by a little infinitesimal amount, ds. How does f change? What is the infinitesimal change in f in response to that move? Well, my point is ultimately moving here from P to this point, just a tiny ways down the road. It's changing its x-coordinate a little bit, its y-coordinate a little bit, and its z-coordinate a little bit, all in these infinitesimal amounts. And to get from here to here, just imagine what's happened. Because the x-coordinate has changed just this tiny little bit, how much does the change in x, just the change in x alone, change the value of f? Well, we know the partial with respect to x. That is our little local multiplier that tells us how small changes in this direction affect the value of f. So we're going to multiply that by the actual distance in the x direction that we have changed, which is dx. Well, the exact same thing is going to happen 2 times more. Namely, as we move from this point to this point, we have changed a certain amount in the y-coordinate. Well, when we do that, we have a multiplier that tells us how the value of f is affected by such changes. That multiplier is the partial of f with respect to y, and we're going to multiply that by dy, the actual distance we have traveled. And of course, as we move from here to here, the z-coordinate has changed, and we know that nudges in the z direction have a local multiplier, partial of f with respect to z, so we're going to get a third term. Okay, and you may be unhappy because we went from something nice and tidy to something rangy and messy over here, but this is nice and tidy only conceptually. We didn't really know how to compute something like this. This is going to help us compute. We can put this into another form that will help us immensely. First thing I want to do is, rather than think of this whole thing as division by ds, let's do it as multiplication by 1 over ds. But look at that top. I'm going to rewrite it. It looks like a dot product. Namely, this dot product, a dot product of 2 vectors, one of which is this little infinitesimal vector right there, and the other of which is something we talked about a few minutes ago. This is that gradient vector of f evaluated at P. So let me rewrite that again, like that. Now I'm using that notation for the gradient that I introduced a few minutes ago. Now I want to concentrate on this second bit. We've got this little infinitesimal vector in the direction of u divided by ds, that little infinitesimal bit of length. Now we said a moment ago that ds is actually the length of that infinitesimal vector, putting this and this together. Writing this down, we can rewrite this stuff in this fashion. And why do I do that? Because think back to what we were talking about a little while ago, about making a unit vector. We take a vector and divide by its own length, and we get the unit vector in the direction of that vector we started with. Well, here I've got a vector. I divide by its length, so I should get the unit vector in the direction we started with. Well, what is the unit vector in that direction? Well, it's u, of course. So that means this whole thing can be replaced by the unit vector u. And now I have come up with something very, very simple. For this directional derivative, I have this very simple expression here. The directional derivative of f at p in the direction of the unit vector u is the gradient of f at p dotted with that unit vector u. This is nice and compact, just like this was nice and compact, but we didn't know what to do with this. This is not only nice and compact, but we can actually compute these things. It's easy to compute a gradient. It just means taking some partial derivatives and then evaluating them at this point. And it's easy to take a dot product. So this is something we can actually compute very easily. Let me summarize this, and then we'll do an example or two. So here is the little theorem we just proved, or the formula we just derived, if you want to say it that way. Once again, to compute the directional derivative of f at p in the direction u, you take the gradient of f at p and dot it with the unit vector u. Important, once again, that we have a unit vector here. Go back and look at the very end of that derivation. You'll see it was crucial that we used a unit vector. All right, here's our concrete example. Let f be our function of three variables, x squared y plus z squared. We want to find its directional derivative at this point 1, 2, 3 in the direction of this vector 3 minus 2, 1. So remember what's happening. If we're looking just at the domain of f, we're starting at this point 1, 2, 3. Let's just say it's right here. We want to know the rate at which the function f, the value of this function, is changing as I move in that direction. So you could think of this point as having a certain temperature, which is going to change as we move here. We want to know the rate at which it's changing in that particular direction. Okay, well, this is not hard after we came up with this recipe right here. The first thing we need to notice is that I haven't specified the direction as a unit vector. I've just given it as a vector whose length certainly is not 1. Rescaling is very easy. We know that the unit vector in the specified direction is the given vector divided by its own length. And a quick calculation shows that that length is the square root of 14. And I'm going to leave that 1 over square root of 14 just hanging outside that vector. I'm thinking of this whole thing is the unit vector. I've just pulled that factor outside because it's going to make the subsequent calculations easier. And let's give that vector a name. Let's call it u hat. Now we can say that by the formula for directional derivatives that we just proved is the gradient of f at the point 1, 2, 3 dotted with the unit vector that we just found. Well, we already know the unit vector, so now I just have to find the gradient, evaluate it at 1, 2, 3, and take the dot product, and we'll be done. Now, to get the gradient at 1, 2, 3, we just need to find the gradient in general, and we remember how that works. The first component of the gradient is the partial of f with respect to x, which is going to be 2xy. The second component is the partial of f with respect to y, which is x squared, and the third component is the partial of f with respect to z, which is 2z. So from that, it follows that the gradient evaluated at 1, 2, 3 is going to be the vector 4, 1, 6, which we get by popping those coordinates into that vector right there. Hence, it follows that the derivative we're looking for is the dot product of that gradient and the unit vector in the direction we're taking the derivative in. You'll remember from the dot product lecture that we can pull constants like this out and take care of that last, so that this becomes 1 over root 14, 4, 1, 6, dotted with 3 minus 2, 1. As for the dot product, that's going to be 12 minus 2, which is 10, plus 6, which is 16. So when we put all that together, we are going to get 16 over root 14, which, in case anybody is interested, is about 4.3. So we have our directional derivative. That means that if we start here at point 1, 2, 3 and move in this direction, then for each infinitesimal unit we move in this particular direction, f's value increases by about 4.3 units. So if f represents temperature and you walk in this direction, well, it's going to be getting hotter. And that's all there is to it, just following this simple recipe right here. Maybe we'll do one last example, and this one will be a function of two variables. Let's find the directional derivative of this function. This is one we've played with before, z equals x squared plus y squared, at the point 1, 1 in the direction pointing back at the origin. So we might be thinking of the domain as something like this. We're at point 1, 1, and the function has a certain value at 1, 1. In fact, it would be 2 when we pop those in there. Say it's 2 degrees, and now we're walking in this direction, back towards the origin. What would the rate of change of the function be in that direction? Well, we recall our theorem for computing directional derivatives. It has two ingredients. We need a unit vector in the direction we're moving, and we need the gradient of the function whose derivative we're finding evaluated at the point in question. Okay, let's start with the gradient. Now, z is a function of x and y. I might make this explicit by saying z is a function of x and y, just so I introduce the f into this problem, and what I write down subsequently makes sense. So we're starting with a gradient. So the gradient of f in this case is a function of two variables, is clearly going to be 2x, 2y, because that's the partial with respect to x, and that's the partial with respect to y. So that means that the gradient evaluated at 1, 1 is going to be 2, 2. So that's a good start. We're going to need that shortly. But we're also going to need the unit vector in this direction. Well, what's that going to be? First off, we can easily get the vector right there, pointing from 1, 1 back to the origin. That vector is clearly going to be minus 1, minus 1. All right, but that's not a unit vector. The length of that is the square root of 2. The unit vector in the direction we are moving in is going to be, let's call it u hat. It's going to be 1 over root 2, and the vector minus 1, minus 1. Let's go ahead and pull that negative out because that's unpleasant to deal with. Okay, so there is the unit vector we're working with. Thus, by our directional derivative formula over here, we have that the directional derivative of f at 1, 1 in the direction of u, which we know is the gradient of f at 1, 1 dotted with that unit vector, is going to be 2, 2 dotted with minus 1 over root 2, 1, 1. And we know that we can dot those first and then put in the scalar by our properties of dot products. So the result will be minus 1 over root 2, and then this dot product is going to give us 2 plus 2, which last time I checked is 4. So we get minus 4 over root 2, which should simplify if we rationalize that. That would be what? Minus 4 over root 2? Yeah, definitely. So minus 2 root 2. Let's do that. That is our directional derivative. Now, it just so happens that because we have a function of two variables in this case, we can interpret this geometrically in terms of the graph of this function. And we know what the graph of this function is. We've looked at it several times. This would be a elliptic paraboloid with circular cross sections. In fact, it would look like this. Now, I've written these, I've moved the axes into a somewhat unconventional position because it'll be easier to see what's going on. We've got 0.11, and we know that the value of the function f there is going to be 2. Now, in this problem, we're walking straight towards the origin. We're walking along that path right there. And what we have concluded is that as we walk in this direction, the value of the function is being reduced. For every infinitesimal step we take in this direction, the value of the function falls by 2 root 2 times that little infinitesimal bit. And those are approximations if those are small real bits. Now, this makes perfect sense when we see the picture. Obviously, the value of the function, if we're representing that by the height of this surface, yeah, as we walk in that direction, it's falling. We can't necessarily see the 2 root 2, but we clearly see where the negative sign is coming from in that case. Okay, that is about it for directional derivatives. So until next time, auf Wiedersehen.